Here we're going to look at a process which we're all familiar with, ice melting. So for this problem we want to imagine that we start with a glass that has a certain amount of solid ice, 36 grams, and initially the ice is at a temperature of 0 degrees Celsius. We're going to imagine leaving this glass of ice in a room that has a constant temperature of 25 degrees Celsius, and the ice will spontaneously melt, and you'll end up with all liquid water at 25 degrees C. So for this process we want to calculate the entropy change for the ice melting and increasing to a temperature of 25 degrees C for the system, the surroundings, and the total entropy change. So to begin with, the very first thing we want to do is always identify what our system is and what the surroundings are, and it can be useful to make a sketch, and so we can do that. So here I can imagine I have my glass, and inside my glass I have some hunk of solid ice, and so I know that it's solid and it's 0 degrees C, and outside there's a room and it has a constant temperature of 25 degrees C. So for this particular case, our room is going to be the surroundings, and we don't know anything about them except they have a constant temperature of 25 degrees C, and our system is going to be the water. And initially the water is going to be solid, and then eventually it's going to turn into a liquid. So with that we can think about the second part of the problem that says identify our initial and final states, and we want to think about this process as happening in two steps because we really have two things happening. We have a phase transition and we have a temperature change, and we want to break that up into two pieces, both to calculate the enthalpy and to calculate the entropy. And so we start out with our solid water, and it's going to be solid and it's going to be 0 degrees C. And the first thing that happens is that we then melt it and we end up with liquid water, and it's still at 0 degrees C. And then finally we warm up the water and it's liquid, and now it's 25 degrees C. And so for all of these processes we're going to think about step 1, the phase transition, and then step 2, the warming process. So let's imagine the energy change for the process. Does the energy change flow into or out of the system? And in both cases we have energy which is flowing from the surroundings at 25 degrees C into the system, which is at a lower temperature. So initially it's at 0 degrees C, and then it eventually equilibrates and comes up to 25 degrees C. But until then, the energy is always flowing from the surroundings into the system. And this happens in the form of heat only. In this process, maybe there's a little bit of work because technically the volume of the liquid and the volume of the solid are a little bit different, but it's very small change. And so here we'll imagine all of the changes are occurring in terms of heat. So our next question is, how much heat? The heat is related to the change in the enthalpy, and so for the change in the enthalpy we want to know what is the heat that flows in for the process. And again, we want to imagine this happening in two steps. First is the phase transition, and second is the warming. So for the phase transition we want to think about the delta H for that process, and that's simply given by the enthalpy of fusion, which is in the problem. But this is a quantity per mole, so we need to know how much it is for our 36 grams. In addition, enthalpies of fusion are given in kilojoules, and so we want the whole process in kilojoules, and so for that we'll just keep it here as 6.02 kilojoules, and that's for a mole, but we don't have 1 mole. Instead we have 36 grams. So we need to be able to convert from grams to moles, and so to do that we have 1 mole of our substance is 18 grams based on the molar mass of water, and we have 36 grams. And so running through that, our moles will cancel, our grams will cancel, and we'll end up multiplying this number by 2, and we get 12.04 kilojoules for the heat for that process. For the second process, this is just the warming of the water. So the warming of the water is a heat for a temperature change, so that's the heat capacity times the change in the temperature. The heat capacity is the extensive heat capacity. We need to know the heat capacity of 36 grams of water. And we're given the heat capacity of water as 4.184 joules, and that's per gram per degree Celsius. So we multiply that by 36 grams and our temperature change, which is 25 degrees Celsius, and those all cancel, and we end up with something which is 3,766 joules, or 3.766 kilojoules. So the total enthalpy then is just the sum of these two, delta H1 plus delta H2, the enthalpy for the phase transition plus the enthalpy for the heating, and we get it's 15.806 kilojoules. So now we want to look at the change in entropy for this process. What's the change in entropy for the melting of the ice? What's the change in the entropy for the warming? So again, we have to think about breaking this into two steps. So to calculate the entropy change for a phase change is very straightforward. It's the enthalpy change for the phase change divided by the temperature. And in this case, that's going to be the enthalpy of fusion for water multiplied by the number of moles that we have divided by the temperature of fusion, or the melting temperature. Because this transition occurs not at 298, but for the system it occurs at 0 degrees Celsius. And so that's going to be 6,020 joules per mole times 2 moles, 36 grams is 2 moles, divided by the temperature, 273.15 Kelvin. And that comes out to be 44.1 joules per Kelvin. For the second phase transition, the second entropy change, second entropy change is a heating change. That's just the heat capacity times the natural log of the final temperature divided by the initial temperature. The heat capacity is again the extensive heat capacity, 4.184 joules per Kelvin per gram, divided by, multiplied by the 36 grams that we have in our sample, times the natural log of the final temperature, 298.15 Kelvin, divided by the initial temperature, 273.15 Kelvin. When we calculate that all out, we get a positive 13.2 joules per Kelvin. So the entropy change for the system is just then going to be the entropy change for these two processes added together, which is 41.4 plus 13.2, and we get a total, an increase in entropy of 57.3 joules per Kelvin. What about the entropy change of the surroundings? The entropy change of the surroundings is related to the heat from the perspective of the surroundings, and remember that here we have energy which is leaving the surroundings, and so are going from the surroundings into the system. And therefore we know that the entropy change for the surroundings is actually going to go down. How much will it go down? Well, the entropy change for the surroundings we can find because it's negative the heat from the perspective of the system divided by the temperature of the surroundings. We did this earlier when we calculated the enthalpy change, so this is actually minus 15,806 joules divided by the temperature of the surroundings, 298.15 Kelvin, and we see that this one is going down minus 53 joules per Kelvin. So what about the entropy change for the universe for this process? Well, we know it's spontaneous and it has to be positive. We can see that because we can calculate the total, or the universe, is simply the entropy change of everything, which is the system plus the surroundings, and we did those two separately, and the system went up 57.3, but the surroundings went down by 53. But you can see the surroundings went down less than the system went up, and there's a net change of 4.3 joules per Kelvin. Now that's the total extensive change in the entropy. That's how much happened for our 36 grams. But if we wanted to know in general for ice melting from 0 degrees and ending up at 25 degrees, what would it be? Well, we have 36 grams of water, which is 18 grams per mole. We have 2 moles of water. And so we could also say that the total entropy change is equal to 4.3 joules per Kelvin divided by 2 moles. It's just half that, 2.15 joules per Kelvin per mole. So now we've merely verified that this process is spontaneous. We all know that ice melts at room temperature, but here you can see that ice melts at room temperature. Why? Because it leads to a total increase in the entropy.